k over t. In other words, we've just proven this relation. It's an important relation that you'll need to remember. Let's go back and look at that in a little bit more detail. We've shown that x of d of omega is a scaled by t version of a periodic replication of xa of omega, where we stretch the frequency response to go from we stretch the frequency response by a factor of capital T. So pictorially, to give you an idea, if I have a discrete time, continuous time signal that has continuous time Fourier transform x of omega that's, say, band limited to plus or minus b in radians, then what this equation is saying is we take this original picture, we scale it. If it originally had height 1, we now scale it in height to be 1 over t. What used to be a function of omega, we now write as a function of omega over capital T. So this is b and minus b, and this is 0. But if I want this not to be a function of omega over capital T, but rather a function of omega, I then have to multiply this axis by capital T. So if I want to write this as a function of omega, then this becomes b times t and minus b times t. 0 times t is still 0. This is height 1 over t. Now, suppose that b was less than pi over t, then this frequency pi over t, when I multiply by t, becomes pi, and minus pi over t becomes minus pi. Now, in the omega over t axis, I have this same picture copied every 2 pi. So I would write this as omega minus 2 pi k over t. So I would have whatever appeared centered at capital omega equals 0 or at omega over t equals 0 will also appear with a copy at omega over t equal 2 pi k over t. So I'll get a copy also of height 1 over t. And this will be 2 pi over t minus b. This will be minus, and this will be 2 pi over t plus b. And in the omega axis, just multiplying everything by b, this also scaled by 1 over t. This appears at 2 pi. This frequency is 2 pi minus b times t, and this is 2 pi plus b times t. That's our leftover from before. And I also have a copy sitting at minus 2 pi. This is periodic with period 2 pi over t in the omega over t space. And in omega, it's periodic with period 2 pi. So this fundamental relation tells us that the discrete time Fourier transform can contain all the information of the continuous time Fourier transform. And in particular, if you notice, if the continuous time Fourier transform x of omega has all of its energy inside the range minus pi over t to plus pi over t, if I focus my attention in here, and if xa of omega were band limited to live in this range minus pi over t to pi over t, then all of the information about x of omega is contained in x sub d of omega in the range minus pi to pi. So in particular, if x of a of omega is 0, for the magnitude of omega greater than or equal to pi over t, then x sub d of omega is related to x sub a of omega by this simple relation. X sub d of omega is just a scaled version, 1 over t, times x sub a of omega over t, in the range minus pi to pi. What happens outside of this range? Well, we know that all discrete time Fourier transforms are periodic with period 2 pi. So in the range minus pi to pi, it's just a scaled by t version of a stretched by t version of xa of omega. And then outside that range, it just repeats. So this complicated formula that includes all these periodic replications all reverts down to this nice, simple transformation, just a scaling and a stretching of the analog Fourier transform, if the signal xa of omega is band limited to plus or minus pi over t. So let's look at that again a little bit closer. So if x sub a of omega has all of its energy between minus b and b in radians, and if we're sampling this signal with an ideal continuous to discrete converter such that t is less than 2 pi over 2b, so it's 2 pi over 2b is the spectral width of the signal in the frequency domain, which is pi over b. In other words, if 1 over t is greater than b over pi, this is just the same thing as 2b over 2 pi. This is 2b over 2 pi. This is the width of the spectrum of xa in hertz. 2b is the width of the spectrum in radians, but if I divide by 2 pi, I get it in hertz. So I need 1 over 2 pi to be greater than the spectral width of the signal, or the bandwidth of the signal. This is the bandwidth of the signal. Then my simple relation holds that in the range minus pi to pi, xa of omega just becomes a scaled version by 1 over t of a stretched version by capital T